We're now going to look at the spherical conductor again and put the electric field and the voltage graphs one on top of the other to take a look at the similarities and differences between them. So with the spherical conductor, so just a metal ball, so that's our blue metal ball that I have shown here, right? It has a radius of 1 meter, so that's our radius of 1 meter, and the electric field is 0 inside of the conductor. So that's our E equals 0. And we know the electric field outside of the conductor is, of course, KQ on R squared. So our E max is the KQ on capital R squared. We could use Gauss's law to derive that. So this is our graph for the electric field. Wonderful, that we understand. Well, the reason that I put this page of notes in here is because we get a little bit of a different result for the voltage. Not just the fact that the function changes from 1 on R squared to 1 on R, which of course it does outside. So we're again looking at the spherical conductor, the radius R equals 1 meter. We see that the graph, the voltage goes as 1 on R, KQ on R for greater than 1. But now that we understand that the electric field is negative the derivative of the voltage, E equaling 0, which it does, right? So 0 electric field does not mean that the voltage has to be 0. It could be 0, but all it's really telling us is definitively that the voltage is constant. So when we come in from infinity and we're increasing voltage, and that's why it's always important that you start your analysis, not just your calculation analysis, but even your conceptual analysis, when thinking about voltage outside of charge distributions, come in from infinity and let the voltage change according to the equation. So it's going to get bigger and bigger and bigger and bigger and bigger based on our KQ on R. Our V max is now right at the surface, but the voltage as we go inside the metal conductor remains the same. It's constant. In this case, it would be roughly like the 9 volts I have shown here. So everywhere inside, we have a voltage of 9 volts, constant. So if the V is constant, the derivative gives us 0, we are consistent. So wanted to make sure that that had its own prominent place in our notes because I realize that can be a little hard to wrap our minds around that, 9 volts means no electric field. Well, 9 volts means no electric field if it's remaining at 9 volts. So I will pause it here, let you get your annotations, and we will, of course, move on.